All right, I wanted to spend some time talking about the pedigree for the lab, and if that requires an extension, that is okay. But what I need you to do is go ahead and submit the lab, and then if you see this and realize that you didn't do it right, just resubmit, upload the document for a second time. Okay, so let's see what it says here. It says in the pedigree below, write the genotypes of the individuals who are labeled with numbers, write capital A to represent the dominant allele, and lowercase a to represent the recessive allele. Start by indicating the genotypes of 5 and 6, then use a Punnett square to figure out what the genotypes of 3 and 4 must be. Next, determine the genotypes of 1 and 2, and finally determine the genotype of 7. So let's just examine this, study it for a minute. We see 1 and 2. By the way, the squares represent males and the circles represent females. Whenever there's a line connecting two individuals by the side, it's kind of old-fashioned, but they call that a marriage line. And whenever shapes are connected from the top, they are siblings. So this square is this square's brother. This circle over here is this square's sister. These three are, basically everyone who's connected from the top is a sibling. So all of these down here are siblings. All of these here are siblings. But these are connected from the side, so they had offspring together. Again, it's called a marriage line. Who knows if these people are married? It's kind of old-fashioned. But let's start by studying this again. So we see that 1 and 2, the parents of 5, do not have the condition. But 5 does have the condition. And like I said, this is I think I said this in a different lecture, but it's very sort of medical sounding, has the condition. But this could just mean that they have blue eyes, right? This could mean that they have blonde hair. This could mean that whatever the condition is, whatever you're talking about, number 5 has it and number 6 hasn't, but their parents don't. 1 and 2 don't. 3 and 4, who the parents of 6 don't have it. So this is a recessive trait. I'll say that again. This is a recessive trait. How do I know that it's a recessive trait? Well, because 5 has it, but neither of 5's parents have it. 1 and 2 do not have this condition. And you could also say, well, 6 has it, but neither of 6 parents have it. So it has to be recessive. So I'll just go ahead and write in number 5's genotype here. Oopsie. We do the same thing for number 6. Just put their genotype right down there by them. So how do we know it's lowercase a, though? How do we know it's not capital A, lowercase a? Like, what evidence do we have to suggest that? Well, what we have to suggest that is if their genotype was something like this, then they wouldn't have the condition, right? If you have the dominant allele, or if you have 2 dominant alleles, then it's impossible for you to have a recessive condition. So we're going to say both of these are lowercase a, and I'm just going to stick the alleles below them, stick their genotype below them. So what is this person's phenotype? What's number 5's phenotype? They have the condition. What is their genotype? They are homozygous recessive. All right, now let's think about what number 1 and 2 kind of have to be. Actually, we'll keep doing this in order. Start to indicate the genotypes of 5 and 6. We did that. Then use a Punnett square to figure out what the genotypes of 3 and 4 must be. Okay, so let's think about this. We make ourselves a corny little Punnett square over here. There's a Punnett square right here. So let's just say we don't know anything about the parents. Let's assume they're both homozygous recessive. So what possible offspring can they have? Well, they can only have homozygous recessive offspring, so it makes some sense. And I guess we're thinking about 3 and 4 here because that's what it asks us to do. It makes some sense. It is possible for them to be homozygous recessive until you look at these individuals. You can see here clearly that they aren't homozygous recessive. How do you know that? Well, you look at them. You walk up to them and say, hey, Bob, hey, Sally, I see that you're not homozygous recessive, and you know that their genotypes cannot be this and this. What could they be? Well, let's say one of them is heterozygous. Is this a possibility? Well, sure, except again, you can see that they are both. Neither of them is homozygous recessive, right? So you know that each parent has to have at least one capital A. So when we look at this Punnett square, where both parents are heterozygous, does it make sense? Yeah. In short, they have one offspring out of the 4 that is homozygous recessive, and then most of their offspring have that dominant allele, right? Most of their offspring have that dominant allele. So, and I wanted to point out here too that just because the odds of them having an offspring, the odds are that they will have one offspring that is homozygous recessive. But it is absolutely possible that all of their offspring are homozygous recessive. Or it's also possible that all of their offspring are homozygous dominant or heterozygous. These are just probabilities. Okay? It just like if your parents had 4 kids, it doesn't mean they're going to have all 4 combinations. These are just the odds. Okay, so we know now that 1 and 2 are heterozygous. How did we know that? Well, they have offspring that have the condition, but they themselves do not have the condition. I'll stick to my conventions and put these underneath. Okay, so there's our Punnett square for like the first part. Build one for the second part here. Actually, I'm sorry, that was supposed to be for 3 and 4, now that I think about it. So yeah, 3 and 4 are supposed to be heterozygous. But the same logic applies to 1 and 2 as well. Okay, so now let's think about number 7. So we know that number 7, one of their parents is homozygous recessive, right? Because again, you can see that phenotype. You can just walk up to that person and be like, yep, I see that you have that condition, you have that characteristic. Or, I guess I shouldn't say you can just walk up to them and see this. But, you can do a medical test. It's an observable trait. It's something that can be ascertained about someone. So, now, what do we know about this person? All we know about this person, because they're from a different family, right? All we know about this person is that they have at least one uppercase A. Their other allele is a question mark. We don't know. We are not sure. Stupid thing. Yeah, that's all we know about them is that they have one uppercase A. How do we know that? Because again, they don't have the condition. So then we can take this and put it over here. And we can build a little Punnett square from this. Let's get in the table itself. Sorry, it's a little wonky. So here are the possible offspring that they have. But actually, we have more information about number 7. We know one more thing. We know that they got at least one lowercase a. How do we know they got one lowercase a? Well, that's all their mom had to give them. That's all that mom had to give. We also know one more thing. We know that they have at least one uppercase A. How do we know they have an uppercase A? Because they don't have the condition. And so this person is for sure heterozygous, without a doubt. They had to get one lowercase a from their mom, and they had to get their uppercase A from their dad.